Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something to ponder as you settle in. Right now, as you're listening, you're hurtling through space at an astonishing speed, completely unaware of it. You're not just sitting still, you're a passenger on a colossal spinning sphere, and that sphere is simultaneously rushing around a star at breakneck speeds, all while that star and its entire galactic neighborhood are themselves sweeping through the cosmos. Think about the sheer audacity of this. Your body, every cell within it, is participating in a cosmic ballet of incomprehensible velocities, yet you feel absolutely nothing. There's no wind in your hair from the Earth's rotation, no dizzying sensation from our orbital sprint around the Sun, no crushing G-forces from our galaxy's journey through the universe. This isn't just a quaint fact, it's a profound testament to the elegance of physics and the incredible stability of our cosmic home. We are moving, always moving, at speeds that would tear apart any terrestrial vehicle, yet we remain perfectly grounded, perfectly comfortable. The ground beneath you, the air you breathe, the clouds above, all are moving in concert, locked in a magnificent silent dance. It's a subtle constant of foundational truth that dictates our days and nights, our seasons, and even the very shape of our planet. Understanding how Earth moves isn't just about knowing astronomical facts. It's about grasping the invisible forces that shape our reality, the subtle mechanics that allow for life, and the deep interconnectedness of everything from the smallest grain of sand to the most distant galaxy. It's a journey into the fundamentals and nature of existence, revealing a universe far more dynamic and intricate than our static perceptions might suggest. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night, connecting us through the shared wonder of the cosmos. Let's start with a question that seems almost absurdly simple, yet holds a profound secret about the nature of motion itself. Why don't we feel the Earth spinning? It's a question children often ask, and it contains a fundamental truth of physics. Right now, as you lie still, you might feel a gentle stillness, perhaps the subtle shift of your own breath, or the distant hum of your environment. But beneath this perceived calm, our planet is performing an astonishing pirouette. At the equator, the surface of the Earth and everything on it, including you, is moving at approximately 1,037 miles per hour, or about 70 kilometers per hour. That's faster than the speed of sound. As you move towards the poles, this speed gradually decreases, until at the north and south poles themselves, your rotational speed would be effectively zero, a mere pivot. Yet across this vast range of speeds, we perceive no motion at all. This isn't just a quirk, it's a fundamental principle of physics at play, a silent, constant demonstration of inertia that allows our lives to unfold on a truly grand scale without us ever feeling the dizzying ride. To truly appreciate this, we need to distinguish between two fundamental types of planetary motion: rotation and revolution. When we talk about the Earth spinning, we are referring to its rotation. It's turning on its own axis, much like a dancer twirling. This rotation is what gives us our day and night cycle. One complete rotation defines one day. The Earth also revolves around the sun, meaning it travels in an elliptical path around our star, a journey that takes approximately 3.25 days, defining our year. For now, let's focus on that invisible constant spin, the rotation that transforms sunlight into shadow and back again endlessly. So why the lack of sensation? The key lies in understanding motion, constant velocity, and acceleration. Imagine you're on an airplane flying at a steady 500 miles per hour. If the flight is smooth and you're not looking out the window, you don't feel that speed, do you? You can walk down the aisle, pour a drink, even toss a coin in the air, and it behaves just as it would on the ground. The reason is that you, the air inside the cabin, and everything else on the plane are all moving at the same constant velocity. There's no sudden change in speed or direction. You only feel motion when there's an acceleration, a change in speed, a change in direction, or both. Think about when the plane takes off, speeding up, lands, slowing down, or hits turbulence, changing direction rapidly. Those are accelerations, and that's when you feel the forces of motion. The Earth's rotation is remarkable. Remarkably continued. It spins at a steady rate, and everything on its surface, including the atmosphere, is carried along with it. We are all moving together as one current system. There are no sudden jerks, no abrupt stops, no sharp turns in our daily spin. The only acceleration we experience from rotation is a very subtle, constant pull towards the centre of the Earth's rotation, which is essentially just a component of gravity. This is why a person at the equator actually weighs ever so slightly less than they would at the poles, because the centrifugal effect of the Earth's spin subtly counteracts gravity. But this effect is so minuscule that it's imperceptible to our senses. Now, how do we know the Earth is spinning if we can't feel it? This is where science moves beyond intuition and into ingenious observation. One of the most elegant and famous proofs of Earth's rotation came in 1851 from a French physicist named Léon Foucault with his eponymous Foucault's pendulum. Imagine a very heavy pendulum, perhaps a cannonball weighing 60 pounds, suspended from an incredibly long wire, say 200 feet long from the dome of a building. Once set in motion, a pendulum, due to its inertia, wants to swing in a single unchanging plane. If you were to draw a line on the floor directly beneath its swing, you would expect it to follow that line indefinitely. But Foucault observed something extraordinary. Over the course of a day, the plane of the pendulum's swing would appear to rotate. If it started swinging north-south, hours later it would be swinging northeast-southwest, and eventually east-west, and so on. This isn't because the pendulum itself is changing its plane of swing. Rather, it's the floor beneath the pendulum, and indeed the entire Earth, that is slowly turning underneath it. At the north or south pole, a Foucault's pendulum would complete a full 360-degree rotation of its plane of swing in exactly 24 hours. At the equator, it wouldn't appear to rotate at all. And at intermediate latitudes, like where Foucault performed his experiment in Paris, the rate of apparent rotation is proportional to the sign of the latitude. This beautiful, slow, undeniable shift in the pendulum's plane of swing is a direct, observable demonstration of the Earth's rotation. It's an aha moment, frozen in time, showing us the invisible dance of our planet. This same rotational force, the one that makes Foucault's pendulum appear to shift, is known as the Coriolis effect. It's not a force in the traditional sense, but rather an apparent force that arises because we're observing motion from a rotating frame of reference, the Earth itself. The Coriolis effect directs moving objects, including winds and ocean currents, to the right in the northern hemisphere and to the left in the southern hemisphere. This is why hurricanes and tropical cyclones spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. The air rushes towards the low-pressure centre of the storm, but as it does, the Coriolis effect subtly nudges it, creating that characteristic swirling pattern. Without the Earth's rotation, there would be no Coriolis effect and our weather patterns would be vastly different, perhaps even less dynamic. It's a constant, subtle influence shaping our planet's atmosphere and oceans. The Earth's rotation is more than just a scientific curiosity. It is the fundamental rhythm of our existence. It gives us the cycle of day and night, marking out our hours and minutes, and anchoring our very perception of time. It sculpted our planet into a slightly oblate spheroid, bulging at the equator and flattened at the poles due to the centrifugal force of its spin. This invisible spin, which we never feel, is the engine of our daily lives, a constant, balanced reminder of our dynamic place in the cosmos. It's a testament to the fact that even when we feel perfectly still, we are always in motion, participants in a grand cosmic waltz. We've begun our journey by understanding the most immediate motion of our planet, its daily spin. This rotation, as we have seen, is responsible for the rhythm of day and night and even shapes our weather. But the Earth's story of motion doesn't end there. Our planet is not just spinning in isolation, it is also engaged in an even grander journey, a vast annual loop around our star. In our next chapter, we will delve into this next layer of motion, the Earth's majestic revolution around the Sun, and how this orbital dance orchestrates the seasons, sculpts our year, and reveals even deeper truths about gravity and the fabric of space-time. And so we've unravelled the invisible spin of our planet, understanding how Earth's astonishing rotation dictates the rhythm of day and night, shapes our winds, and even subtly sculpts our global form. We've seen the ingenious dance of Foucault's pendulum and felt the distant guiding hand of the Coriolis effect. But as fundamental as this daily pirouette is, it doesn't quite explain the grander, slower ballet that unfolds over the course of a year. It doesn't explain the warmth of summer, the crisp chill of winter, or the vibrant transitions of spring and fall. For that, my curious friends, we must expand our cosmic perspective even further. We must acknowledge not just Earth's magnificent spin, but its majestic revolution, its epic journey around our home star, the Sun. Imagine, if you will, not just spinning in place, but also hurtling through the vastness of space, tracing an immense elliptical path around a colossal fiery orb. That's precisely what you're doing right now as you listen. You are not just standing still. You are a passenger on a spaceship called Earth, orbiting the Sun at an average speed of approximately some 67,000 miles per hour. Let that sink in for a moment. 67,000 miles per hour! To put that into perspective, that's roughly 100 times faster than the fastest bullet trains on Earth. It's about 30 times the speed of a commercial airliner at cruising altitude. It's a velocity that utterly dwarfs anything we experience in our daily lives. A speed that should, by all accounts, be tearing us apart or at least pinning us to the back of our cosmic vehicle. Yet here we are, sipping our coffee, walking our dogs, or simply gazing at the sky, completely oblivious to this breathtaking velocity. Why? The answer, once again, lies in the elegant simplicity of physics and the principle of constant velocity. Just as with Earth's rotation, our orbital journey around the Sun is remarkably smooth and consistent. We, along with every tree, every ocean, every cloud, and every molecule of air, are all moving together at the same incredible speed, in the same grand direction. There are no sudden accelerations, no jarring stops, no sharp turns that would register with our senses. We are simply part of the ride, a cohesive unit within this cosmic express. This constant, steady motion is a testament to the profound stability of our solar system, a system honed over billions of years into a delicate offense of gravitational force. We are caught in the Sun's immense gravitational embrace, pulled along its invisible tether, preventing us from simply flying off into the cold, dark void of interstellar space. It's a cosmic waltz, a gravitational dance of incomprehensible velocities, yet one that feels utterly motionless to us, its participants. So we're flying around the Sun at an incredible speed. But how does this grand orbital journey bring us our seasons? Here's where we tackle one of the most persistent and widespread misconceptions in astronomy. Many people assume that seasons are caused by Earth being closer to or farther from the Sun at different times of the year. And it's a perfectly logical assumption, isn't it? It feels hotter when you're closer to a heat source. However, this is not the primary reason for our seasons. In fact, Earth's orbit around the Sun is indeed elliptical, meaning our distance does vary. We are actually closest to the Sun, a point called perihelion, in early January, right when the Northern Hemisphere is experiencing winter. Conversely, we are farthest from the Sun, a point called aphelion, in early July, when the Northern Hemisphere is enjoying its summer. If distance were the sole factor, both hemispheres would experience the same season at the same time, which, as we know, is certainly not the case. When it's summer in New York, it's winter in Sydney. When flowers bloom in London, snow falls in Buenos Aires. The true, elegant and utterly brilliant explanation for our seasons lies not in our distance from the Sun, but in a subtle yet profound characteristic of our planet, Earth's axial tilt. Imagine our planet as a colossal spinning top. Now imagine that top isn't standing perfectly upright relative to its path around a central point. Instead, it's leaning over slightly. That's our Earth, our planet's axis, the imaginary line running through the north and south poles around which it rotates, is tilted at an angle of approximately 23 degrees relative to its orbital plane, the flat plane in which it revolves around the Sun. This tilt is constant, always pointing in the same direction in space towards the star Polaris, our North Star, as Earth makes its year-long journey. And this tilt, my friends, is the grand orchestrator of our seasons. Think of it like this. When one hemisphere, say the Northern Hemisphere, is tilted towards the Sun, it receives the Sun's rays more directly. Picture a flashlight beam. If you shine it straight down onto a surface, the light is concentrated into a small, intense circle. This direct sunlight means the energy is focused over a smaller area, leading to higher temperatures and more efficient heating. Furthermore, when a hemisphere is tilted towards the Sun, that hemisphere also experiences longer periods of daylight. The Sun appears higher in the sky and its rays travel through less of Earth's atmosphere, losing less energy along the way. This combination of direct sunlight and extended daylight hours brings us summer. Conversely, when that same hemisphere is tilted away from the Sun, the sunlight strikes it at a more oblique or slanted angle. Now that flashlight beam is spread out over a larger area, diluting its intensity and making it less effective at heating the surface. The Sun appears lower in the sky, its rays travel through more atmosphere, and the days become significantly shorter. This combination of indirect sunlight and diminished daylight hours brings us cool winter. And what about the other hemisphere? It's experiencing the exact opposite. When the Northern Hemisphere is tilted towards the Sun for summer, the Southern Hemisphere is simultaneously tilted away, experiencing its winter. This beautiful inverse relationship is the smoking gun that proves the tilt, not distance, is the key. As Earth continues its revolution, there are two special points in its orbit when neither hemisphere is tilted significantly towards or away from the Sun. These are the equinoxes, Latin for equal night. During the vernal spring equinox, around March 20th, and the autumnal fall equinox, around September 22nd, the Sun's direct rays fall precisely on the equator. At these times, day and night are roughly equal in length across almost the entire planet, and the temperatures are generally moderate, marking the transitions between the extreme temperatures of summer and winter. Then we have the solstices. These are summer solstice, around June 21st in the Northern Hemisphere, marks the moment when that hemisphere is most directly tilted towards the Sun. It's our longest day of the year, and the Sun reaches its highest point in the sky. 6 months later, the winter solstice, around December 21st in the Northern Hemisphere, is when that hemisphere is maximally tilted away from the Sun, resulting in the shortest day and the lowest Sun angle. These are the peaks and troughs of our seasonal cycle, driven entirely by that unwavering 23.5 degree lean. This constant tilt, maintained throughout our elliptical journey, is not just responsible for the changing temperatures and daylight hours we experience. It's fundamental to the very fabric of life on Earth. It dictates our climate zones, influences agricultural cycles, triggers the migrations of countless animals, and has profoundly shaped human cultures, traditions, and even our architecture for millennia. Without this tilt, Earth would be a very different place. Perhaps a world with little seasonal variation, or extreme heat at the equator and perpetual cold at the poles. The delicate balance of life as we know it is intimately tied to this elegant cosmic lean. So as you gaze at the changing leaves in autumn, feel the warmth of a summer sun, or bundle up against a winter chill, remember the silent, majestic force at play. You are not just standing on a spinning sphere, you are a participant in a grand year-long voyage, carried by a planet whose subtle lean transforms the very essence of our experience. The Earth's revolution around the Sun, guided by its constant axial tilt, is another profound example of the hidden mechanics that make our world so dynamic, so diverse, and so incredibly alive. Isn't it astonishing to consider the intricate dance of our planet, constantly moving, constantly changing, yet providing such a stable and predictable home for us all? The universe in its vastness is full of such wonders, and we're only just beginning to truly appreciate the subtle elegance of how Earth moves. If you're as fascinated as we are by these cosmic revelations, be sure to hit that like button and subscribe to Dreamy Science for more journeys into the unseen marvels of our universe. And please drop a comment below. What's your favourite season, and has learning about the axial tilt changed how you think about it? Next time we'll delve even deeper, exploring how other celestial bodies, like our own moon, influence Earth's movements and in turn our very existence. Our journey through Earth's unseen movements has revealed a colossal spinning sphere perpetually twirling and hurtling through the cosmos. We've uncovered the constant unfelt rotation that crafts our days and nights, and the majestic revolution that orchestrates our seasons. But our planet, magnificent as it is, does not embark on this cosmic ballet alone. It has a constant companion, a silent guardian that influences our very existence in ways both profound and subtle. We are talking, of course, about the moon. Imagine, if you will, that you are not just a passenger on a spinning, orbiting planet, but that you're also caught in the gravitational embrace of another celestial body, one that circles us as we circle the sun. This is the intricate dance we find ourselves in with our moon. For every dizzying spin Earth completes, for every sweeping orbit around the sun, the moon is there, steadfastly revolving around us. This lunar revolution is a journey in itself, taking our moon approximately 27.3 Earth days to complete one full orbit relative to the stars, what astronomers call a sidereal month. However, for us on Earth, observing its phases, a full cycle from new moon to new moon takes about 29.5 days. This slight difference arises because as the moon orbits Earth, Earth is also moving around the sun. The moon has to travel a little further to catch up and present the same phase to us. And just like Earth's revolution around the sun, the moon's orbital speed is astonishing. On average, our lunar friend zips around us at approximately 228 miles per hour. That's fast enough to cross the continental United States in a little over an hour. So, as you sit here, perhaps sipping your coffee, perhaps gazing out a window, you're not only spinning at over 1,000 miles an hour and orbiting the sun at 67,000 miles an hour, but you are also, along with the entire Earth, being carried around a central point by the moon at thousands of miles per hour. It's a dizzying thought, isn't it? A nested set of movements, each imperceptible yet each fundamental to our reality. But the moon's influence extends far beyond merely adding another layer to our planetary velocity. Its most palpable, most observable effect on Earth is something we experience every single day. Something that shapes our coastlines, guides our shipping, and inspires poets and scientists alike. The tides. What a phase here, tides, Vistla. And how does a distant celestial body, albeit our closest neighbour, exert such a powerful pull on our vast oceans? The answer lies in one of the universe's fundamental forces, gravity. Isaac Newton, that ingenious mind we often credit for so much of our understanding of the physical world, formulated the law of universal gravitation. It states, simply put, that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centres. In plainer terms, the bigger something is, the more it pulls. The closer it is, the stronger that pull. The Moon, while significantly smaller than Earth, is incredibly close to us, making its gravitational grip remarkably potent. Now here's where it gets fascinating. The Moon doesn't pull on all parts of the Earth with precisely the same strength. Because Earth is a sphere, some parts are closer to the Moon than others. The side of Earth directly facing the Moon experiences the strongest gravitational pull. This pull literally draws the ocean water on that side towards the Moon, creating a bulge, what we call a high tide. But wait, if you've ever spent time by the ocean, you know there are typically 2 high tides a day, not just one. How does that second high tide on the side of Earth opposite the Moon come about? This is often the trickiest part of understanding tides, but let's break it down. Imagine the Earth and the Moon as a system orbiting a common centre of mass. As the Moon pulls on the Earth, it's not just pulling the water, it's pulling the entire planet. The solid Earth is pulled towards the Moon more strongly than the water on the far side of the Earth. Think of it like this: the Earth itself is being gently stretched by the Moon's gravity. The water on the side facing the Moon is pulled away from the solid Earth. And on the side opposite the Moon, the solid Earth is pulled away from the water, leaving the water to bulge outwards due to its own inertia, its tendency to resist motion. It's almost as if the Earth is being pulled out from under the water on the far side, leaving that water to accumulate in another bulge. So we have 2 bulges of water, one on the side of Earth facing the Moon and one on the side opposite the Moon. As Earth rotates on its axis approximately every 4 hours, any given location on our planet passes through these 2 bulges. This is why most coastal areas experience 2 high tides and 2 low tides each day. The areas between these bulges where the water has been drawn away experience low tides. Of course, the Sun, being an enormous celestial body, also exerts a gravitational pull on Earth. While it is much, much farther away than the Moon, its sheer mass means its influence is not insignificant. The Sun's gravity also creates tidal bulges, though they are only about half the size of the Moon's. When the Sun, Moon and Earth align, which happens during a new moon, when the Moon is between the Sun and Earth, and a full moon when Earth is between the Sun and Moon, their gravitational pulls combine. This synergistic effect leads to especially high tides and especially low tides known as, spring tides. The term spring here doesn't refer to the season, but to the springing forth or surging of the water. Conversely, when the Sun and Moon are at right angles to Earth during the first and third quarter moon phases, their gravitational pulls partially counteract each other. The Moon is pulling in one direction, and the Sun is pulling in a perpendicular direction. This results in less extreme tides, with lower high tides and higher low tides, which we call neap tides. These rhythmic pulses of the ocean, this constant push and pull, are more than just a captivating natural phenomenon. They are a powerful demonstration of the invisible forces that govern our universe, and they have profound consequences for our planet. One of the most remarkable, yet often overlooked, effects of the tides is their role in slowing Earth's rotation. Think of the immense volume of water in our oceans, constantly sloshing and moving under the Moon's gravitational tug. As these massive tidal bulges travel around the globe, they drag against the ocean floor and continental landmasses. This friction acts like a subtle yet persistent brake on Earth's spin. The effect is incredibly small in human terms. Earth's rotation is slowing down by only about 2.3 milliseconds per century. It is not something you'd ever notice in your lifetime or even in many generations. But over vast geological timescales, this adds up. Billions of years ago, when Earth was young, a day was much shorter, perhaps only 5 or 6 hours long. The Moon was also much closer to Earth then. As Earth's rotation has slowed, the Moon has in turn been gradually pushed further away from us, receding at a rate of about 1.5 inches, 3.8 centimeters per year. It's a cosmic dance with a slow, steady separation, a testament to the conservation of angular momentum in the Earth-Moon system. But perhaps the most crucial role the Moon plays in our existence, the one that makes life as we know it possible, is its stabilizing effect on Earth's axial tilt. Remember in Chapter 2 we talked about Earth's 23.5 degree tilt relative to its orbital plane, and how this tilt is the fundamental cause of our seasons. Well, without the Moon, that tilt wouldn't be stable. Imagine a Spitzenwheel. If it's spinning fast, it stays upright. But if it slows down, it starts to wobble chaotically. Earth in his cosmic spin is like that. Without a large nearby companion like the Moon, Earth's axial tilt would not remain fixed at 23.5 degrees. Over millions of years, the gravitational influences of other planets, particularly Jupiter, would cause Earth's tilt to wobble wildly from perhaps nearly 0 degrees to as much as 85 degrees. Think about the implications of such a chaotic wobble. If Earth's axis were to straighten to 0 degrees, we would lose our seasons entirely. The equator would be perpetually scorching and the poles would be perpetually frozen with little variation in between. Conversely, if the tilt increased dramatically, say to 80 degrees, then different parts of the planet would experience extreme seasonal swings, with one pole facing the sun for half the year, and the other pole enduring months of darkness. Such extreme climate variations would create an environment utterly hostile to the development and sustained evolution of complex life. The Moon, in its majestic revolution around us, acts like a giant celestial gyroscope, dampening these wobbles and firmly anchoring Earth's axial tilt. Its substantial gravitational pull provides the stability needed to keep our tilt relatively constant, ensuring a predictable cycle of seasons, moderate climates, and the consistent environmental conditions that allowed life to flourish and evolve over billions of years. This realization transforms our perception of the Moon from a mere pretty orb in the night sky to an indispensable partner in Earth's story. It's not just a barren rock, it's a fundamental architect of our planet's habitability. Its very presence is a direct consequence of a colossal ancient collision. The prevailing giant impact hypothesis suggests that a Mars-sized protoplanet, often called Theia, slammed into early Earth billions of years ago, ejecting a vast amount of material that eventually coalesced to form our Moon. A violent birth indeed, but one that gave rise to a celestial anchor, a guardian of our climate. So the next time you gaze up at the Moon, whether it's a slender crescent or a luminous full disk, remember the intricate dance it performs with our planet. Remember its invisible hand shaping our tides, subtly slowing our spin, and most crucially stabilizing the very tilt that gives us the rich tapestry of our seasons. We are not just moving, we are moving with a companion, a silent partner in this grand cosmic waltz. Our journey through how Earth moves has taken us from the invisible spin of our home world to its sweeping orbit around the Sun, and now to the profound influence of our nearest celestial neighbour. But the universe is vast and our movements are part of an even grander design. In our next exploration, we will expand our perspective even further, venturing beyond the Earth-Moon system to see how our entire solar system itself is in motion, hurtling through the galaxy at speeds that defy imagination. The cosmic ballet continues, and we are all participants. If this journey into the hidden mechanics of our universe has sparked your curiosity and wonder, hit that like button, share this with fellow explorers, and drop a comment below with your thoughts. What aspect of Earth's movements fascinates you the most? Your insights fuel our shared discovery. We've journeyed from Earth's silent spin to its majestic dance around the sun, and then outwards to the moon's profound embrace, stabilizing our world. We've uncovered layers of motion, each one grander and faster than the last, yet all imperceptible to our daily lives. You're now intimately familiar with the fact that you are hurtling through space at incredible speeds, completely unaware of the journey. But what if I told you that all these motions, Earth's rotation, its revolution around the sun, even the moon's orbit around us, are just small components of an even grander, more breathtaking cosmic ballet? Let's expand our perspective once more. Imagine pulling back further and further past the moon, past Earth's orbit, past Mars and Jupiter, past the farthest reaches of our solar system. What do you see? Our sun, a brilliant star with its family of planets, dwarf planets, asteroids and comets all dutifully orbiting it. It looks like a self-contained system, a perfect cosmic clockwork. But here's the mind-bending truth: our entire solar system is on the move, engaged in a colossal journey through space. Our sun, the very star that anchors our existence, is not stationary. Far from it. It's just one of hundreds of billions of stars, all bound together in a magnificent spiral galaxy we call the Milky Way. And guess what? Every single one of those stars, including our sun, is orbiting the gravitational center of our galaxy. Think of it like this: if Earth is spinning and circling the sun, then the sun itself is spinning and circling something even bigger. That something bigger is the supermassive black hole at the heart of the Milky Way, known as Sagittarius A. It's a gravitational behemoth, holding our entire galaxy in its incredible grasp. So how fast are we moving now? If you thought some 10,000 ampere around the sun was impressive, prepare to be amazed. Our sun, along with all of us riding along on Earth, is hurtling through the Milky Way galaxy at an astounding speed of approximately 500,000 miles per hour. Yes, you heard that right, 500,000 miles every single hour. That's about 200 kilometers per second for our metric friends. This isn't just a gentle stroll, it's a cosmic sprint of truly epic proportions. To put that into perspective, imagine an airplane flying at its top speed. Now multiply that speed by hundreds. You're moving 5 times faster than the fastest bullet, all while sipping your coffee, completely oblivious to the incredible velocity. This speed is what allows our solar system to maintain its orbit around the galactic center, balancing the immense gravitational pull with our forward momentum. Our solar system is located about 2/3 of the way out from the galactic center, nestled within one of the Milky Way's spiral arms, specifically the Orion arm, sometimes called the local arm. From our vantage point, the Milky Way appears as a luminous band across the night sky, a breathtaking testament to the billions of stars that form our home galaxy. But we are part of that band, a tiny speck on a grand sweeping arc. How long does it take for our sun to complete just one single orbit around the galactic center? Given the immense distances involved, even at 500,000 km, it takes a truly staggering amount of time. One full lap for our solar system around the Milky Way is what scientists call a galactic year, and it lasts approximately a million Earth years. In Earth. 230 million years. It's a timescale almost impossible for the human mind to grasp. Think about all the changes our planet has undergone in just one galactic year. The last time our solar system was in this exact position in the galaxy, the Earth looked dramatically different. The supercontinent Pangaea was just beginning to break apart. Dinosaurs were only starting to emerge, not yet the dominant life forms they would become. Mammals were tiny, scurrying creatures in the shadows. The Himalayas hadn't even begun to rise, and the Atlantic Ocean was a mere sliver. In the span of one galactic year, continents have drifted across the globe, oceans have opened and closed, mountains have been forged, and entire species have risen, flourished, and vanished. Our planet, as we know it, is a dynamic, ever-changing world, and much of that change has played out over the course of these majestic galactic revolutions. Each galactic year is a chapter in Earth's deep history, a testament to the ceaseless motion and evolution of our cosmic home. This galactic orbit isn't just a fascinating fact, it's a fundamental aspect of our existence. The Sun's position within the galactic disk and its journey through different regions of the galaxy may even influence events on Earth over vast timescales, such as periods of increased cometary impacts or changes in cosmic ray flux. We are truly passengers on a grand cosmic voyage, and our destination is always changing, always moving. But wait, we're not done yet. Just as our solar system orbits the centre of the Milky Way itself is not a lone static island in the universe. Oh no! Our entire galaxy is also on the move, participating in an even larger cosmic dance. The Milky Way is part of a cluster of galaxies called the Local Group. This group is gravitationally bound, meaning all the galaxies within it are pulling on each other. The two largest members of this local group are our own Milky Way galaxy and its colossal neighbour, the Andromeda galaxy. Andromeda is a majestic spiral galaxy, even larger and more massive than the Milky Way, and it's visible to the naked eye as a faint fuzzy patch in the night sky on a clear dark evening. Andromeda is not just a distant neighbour, it's on a collision course with us. Yes, you heard that correctly. Our entire Milky Way galaxy is hurtling towards the Andromeda galaxy at an incredible speed of approximately 250,000 miles per hour, about 110 kilometers per second. This motion is driven by the mutual gravitational attraction between these two galactic giants. It's a truly humbling thought. Two colossal spiral galaxies, each containing hundreds of billions of stars, are rushing towards each other across the vast emptiness of intergalactic space. But before you start picturing a catastrophic cosmic pileup, let's clarify what a galactic collision actually means. Unlike car crashes or planetary impacts, galactic collisions are incredibly slow-motion events that unfold over billions of years, and they are largely empty encounters. The distances between individual stars within a galaxy are so immense that when two galaxies merge, the chances of stars actually crashing into each other are incredibly astronomically small. Imagine two vast swarms of gnats flying through each other. While the swarms intermingle, individual gnats are highly unlikely to collide. Instead, what happens is a magnificent, drawn-out cosmic ballet of gravitational forces. The two galaxies will slowly distort each other, their spiral arms tugging and stretching, eventually merging to form a new, even larger elliptical galaxy. This future galaxy has already been given a name by astronomers, Milkomeda. This grand merger is predicted to begin in about 4.5 billion years, with the most intense phase lasting for another billion years or two. By the time Milkomeda fully forms, our Sun will be much older, perhaps nearing the end of its life cycle, and Earth's fate will be intertwined with this new galactic identity. Our solar system might be flung into a different part of the newly formed galaxy, or perhaps even ejected into intergalactic space, but the stars themselves will mostly pass by each other, influenced only by the combined gravitational fields. So let's take stock of our incredible journey so far. You are currently spinning on Earth's axis at over 1,000 pound-mph, revolving around the Sun at 7,000 pound-mph, orbiting the galactic center with our Sun at 100,000 pound-mph, and along with the entire Milky Way rushing towards Andromeda at 250,000 pound-mph. This means your combined speed through the cosmos is truly mind-boggling, well over 800,000 miles per hour. And yet you feel absolutely nothing. No wind, no g-forces, no sensation of movement at all. Why? Because these are all incredibly stable, constant velocities relative to their respective frames of reference. There's no sudden acceleration or deceleration to make you feel the speed. It's the ultimate smooth ride. We've moved from the subtle tilt of Earth's axis to the majestic dance of galaxies, uncovering layers of motion that reveal a universe far more dynamic and interconnected than we could ever imagine. Each layer builds upon the last, painting a picture of constant, elegant movement. And even beyond the local group, our cluster of galaxies is being pulled towards even larger structures, like the Virgo supercluster, and ultimately towards a mysterious, massive gravitational anomaly known as the Great Attractor. The entire universe, in fact, is expanding, carrying galaxies further apart from each other, a motion on the grandest scale of all, governed by the very fabric of space-time itself. From the unseen spin that defines our days and nights, to the cosmic waltz that sculpts our seasons, to the moon's gentle tug that shapes our tides and stabilizes our world, and now to the sun's epic journey through the galaxy and the Milky Way's impending embrace with Andromeda, every single moment is a testament to the universe's ceaseless, magnificent motion. We are truly living on a dynamic, ever-moving stage, part of a cosmic symphony of incomprehensible velocities and breathtaking scales. Doesn't that just fill you with wonder? To realize the incredible journey you are on every second of every day without ever feeling a single bump or jolt is a profound reminder of our place in the cosmos. A small but significant part of a grand unfolding drama. If this journey through the universe's motions has sparked your curiosity and left you gazing at the stars with a newfound appreciation, then you're exactly where we want you to be. Don't forget to hit that like button, share this with fellow cosmic travelers, and drop a comment below. What aspect of Earth's motion do you find most astonishing? Join us next time as we continue to unravel the hidden mechanics of our universe. Until then, keep looking up and keep wondering. We left off with an astonishing revelation. Our entire local group of galaxies, including our very own Milky Way and its Andromeda neighbour, isn't just drifting aimlessly. Oh no! It's being pulled with an almost irresistible force towards something truly immense. Something we've only begun to understand. This gravitational behemoth, located roughly 250 million light-years away in the direction of the Centaurus supercluster, is known simply as the Great Attractor. Think of it. After all the incredible speeds we've already uncovered, Earth's rotation, our planet's revolution around the Sun, the Moon's dance, the Solar System's galactic orbit, and the Milky Way's hurtle towards Andromeda, we add yet another layer of colossal motion. Our local group, a collection of dozens of galaxies, is streaming towards the Great Attractor at hundreds of thousands of miles per hour. That's right, hundreds of thousands of miles per hour, adding still more velocity to our cosmic journey. But what is the Great Attractor? Is it a supermassive black hole? A cluster of clusters? Well, it's not a single point, but rather a vast, diffuse region of space with an extraordinary concentration of mass. It's a gravitational anomaly, a cosmic whirlpool pulling everything in its vicinity towards its heart. For a long time, its true nature was shrouded in mystery, largely obscured from our view by the dust and gas in the plane of our own Milky Way galaxy, a region astronomers call the Zone of Avoidance. It's like trying to see a distant mountain through a thick fog. We knew something was there because of its gravitational tug, but its exact form remained elusive. However, as our instruments and understanding have advanced, we're beginning to pierce through that cosmic veil. We now understand that the Great Attractor isn't an isolated phenomenon. but rather a prominent feature within an even larger structure, the Laniakea supercluster. The name Laniakea is Hawaiian for immeasurable heaven, and it's a fitting description for a structure that spans 500 million light-years and contains the mass of about 100,000 Milky Way galaxies. Imagine our local group, along with the Virgo supercluster, which the Great Attractor is a part of, are all just threads in this immeasurable cosmic tapestry. This brings us to a mind-bending concept, one that completely reshapes our understanding of the universe's architecture, the cosmic web. For a long time, we thought galaxies were just scattered randomly throughout space like confetti after a parade. But that's far from the truth. Instead, the universe on its grandest scales resembles an enormous three-dimensional web. Picture a vast, intricate network of interconnected filaments and nodes made up of galaxies and clusters of galaxies. These immense filaments stretch for hundreds of millions of light-years, forming cosmic superhighways where matter is concentrated. In between these glowing threads are vast empty regions, colossal cosmic bubbles, almost completely devoid of galaxies. These are the cosmic voids. Our local group, the Virgo supercluster and the Laniakea supercluster, are all just tiny knots and strands within this gargantuan luminous web. The Great Attractor, then, is one of the most massive and influential nodes in our local cosmic neighbourhood, a gravitational nexus where multiple filaments converge, drawing in everything around it like a colossal cosmic drain. It's a testament to the fact that even on the largest scales, gravity remains the ultimate sculptor, shaping the very fabric of existence. But how did such a magnificent and intricate structure come to be? What invisible forces are at play weaving this cosmic tapestry? This is where our journey takes us into the realm of the truly mysterious, the unseen architects of the universe. Dark matter and dark energy. Let's start with dark matter. We've talked about gravity holding planets, stars, and galaxies together. But here's a cosmic conundrum. When astronomers observe how galaxies rotate or how galaxy clusters behave, they find that there simply isn't enough visible matter, the stars, gas, and dust we can detect, to account for the gravitational forces at play. If galaxies only contained the visible matter we see, they would literally fly apart. It's like watching a merry-go-round spinning incredibly fast. If there weren't enough invisible anchors holding the horses down, they'd be flung off into space. This invisible missing mass is what we call dark matter. It doesn't emit, absorb, or reflect light or any other form of electromagnetic radiation. We can't see it, we can't touch it, and it doesn't interact with regular matter in any way we currently understand, except through gravity. Yet its gravitational presence is undeniable. Imagine a colossal, ghostly scaffolding that permeates the entire universe. That's dark matter. It acts as the invisible gravitational glue, the cosmic skeleton upon which the visible universe, the stars, galaxies, and the grand cosmic web has been built. Without dark matter, gravity wouldn't be strong enough to pull matter together into galaxies and clusters, and the universe would be a much emptier, more diffuse place. It's estimated that dark matter makes up about 27% of the total mass and energy of the universe. So for every bit of visible matter you see, there's roughly 5 times as much dark matter silently, invisibly influencing its every move. It's a profound thought, isn't it? That most of the universe is utterly invisible to us, yet utterly essential. Now, if dark matter is the unseen force pulling things together, what about the force that's pushing them apart? This brings us to perhaps the most baffling mystery in modern cosmology: dark energy. For most of the 20th century, scientists believed that the expansion of the universe set in motion by the Big Bang must be slowing down due to the gravitational pull of all the matter within it. It made intuitive sense, right? Like a ball thrown upwards, it eventually slows down due to Earth's gravity. But in the late 1990s, observations of distant supernovae, exploding stars that act as cosmic mile markers, revealed something astonishing, something completely unexpected. The universe wasn't just expanding, its expansion was accelerating. It was speeding up. This discovery was so profound that it earned a Nobel Prize. It implied the existence of a mysterious anti-gravitational force, an intrinsic property of space itself that is actively pushing the universe apart. This force is what we call dark energy. Think of it like this. Imagine you're trying to pull two magnets together, but there's an invisible spring between them that's constantly pushing them apart, getting stronger as the distance increases. That's a bit like dark energy. It's not just stretching the space between galaxies, it's causing the rate of that stretching to increase. It's as if the universe has its own internal engine, constantly hitting the accelerator pedal. Dark energy is even more dominant than dark matter, comprising an astounding 68% of the universe's total energy density. This means that the vast majority of our universe is made up of things we cannot see and do not fully understand. We live in a universe dominated by the dark. So let's put it all together. You right now are a passenger on a planet that is 1. Rotating at over 1,000 miles per hour at the equator. 2. Revolving around the sun at 7,000 miles per hour. 3. Orbiting with the moon at 2,288 miles per hour. 4. Hurtling with our entire solar system around the centre of the Milky Way at 500,000 miles per hour. 5. With the Milky Way towards the Andromeda Galaxy at 250,000 miles per hour. 6. Streaming with our local group towards the Great Attractor at hundreds of thousands of miles per hour. And all of these incredible, multi-layered motions are taking place within a cosmic web, a vast, intricate structure of galaxies and voids shaped by the invisible hand of all dark matter. And to top it all off, the very fabric of this cosmic web, the space between all these galaxies and superclusters, is being stretched and expanded at an ever-increasing rate by the mysterious force of dark energy. It's truly a cosmic ballet of incomprehensible velocities, a majestic revolution within a grand galactic dance, all orchestrated by forces we are only just beginning to grasp. From the gentle tug of the moon on our tides to the accelerating expansion of the entire universe, every single movement, every single interaction is a testament to the elegant, intricate laws of physics. You're not just standing still, you're hurtling through the cosmos at speeds beyond imagination, a tiny speck on a colossal spinning sphere, navigating a universe that is constantly expanding, evolving, and revealing new layers of wonder. The stability you feel is a profound illusion, a testament to the constant velocity and inertial forces that govern our everyday experience. What an incredible journey we've taken together, haven't we? From the imperceptible spin beneath our feet to the stretching fabric of the cosmos, we've unveiled the hidden mechanics of how Earth moves and how everything else moves along with it. The universe is a place of constant motion, of profound mystery, and of breathtaking beauty. And the best part? There's always more to discover, more to learn, more to marvel at. So as we bring our cosmic journey to a close, remember this. The universe isn't just out there, it's within you, and you are an integral, moving part of its magnificent story. Thank you for joining us on this incredible exploration of how Earth moves. Keep looking up, keep asking questions, and keep that sense of wonder alive. If you enjoyed unraveling these cosmic secrets with us, don't forget to hit that like button, share this with your friends, and drop a comment below. What do you think is the most mind-boggling layer of motion we explored today? We'd love to hear your thoughts. And so here we are at the culmination of our journey through the astonishing movements of our home planet. We've spun, we've orbited, we've been swept along by our moon, our sun, our galaxy, and even entire superclusters. We've peered into the profound mysteries of dark matter and dark energy, the invisible forces orchestrating this cosmic ballet. But let's pause for a moment and bring it all together. Do you remember those dizzying speeds? The Earth's rotation at over 1,000 miles per hour at the equator? Our stately revolution around the Sun at 67,000 miles per hour? The Moon's tireless dance around us at 228 miles per hour? Our entire solar system, a tiny speck hurtling around the galactic centre at a mind-boggling 500,000 miles per hour? And then, our Milky Way, along with its local group companions, streaking towards Andromeda at 250,000 miles per hour, all while being tugged by the colossal gravitational anomaly we call the Great Attractor, adding hundreds of thousands more miles per hour to our cosmic velocity. When you add it all up, when you truly let the numbers sink in, you realize that you, right now as you listen to my voice, are not just sitting still. Oh no. You are a passenger on a colossal spinning sphere embedded within a larger system, which is itself a part of an even grander system, all of which is rocketing through the vast expanse of space at a combined, astonishing, almost incomprehensible speed of over 800,000 miles per hour. Let that sink in. 800,000 miles per hour. That's faster than any bullet, faster than any rocket we've ever launched into space, faster than anything you could possibly conceive of in your everyday experience. And yet you feel absolutely nothing. No wind in your hair, no G-forces pushing you into your seat, no sensation of movement whatsoever. It's the ultimate illusion of stillness, a profound cosmic magic trick playing out every single second of your existence. Why don't we feel it? We've touched upon it throughout our journey, but let's bring it into sharp focus now as the sum total of our motions truly highlights this paradox. The fundamental reason, as we learned, lies in the principle of war, constant velocity, and inertia. You see, you, your chair, your house, your entire city, the very air you breathe, all of it is moving at precisely the same speed and in the same direction as you are, relative to the immediate system you're a part of. We are all passengers on the same cosmic ship. There's no sudden acceleration, no abrupt braking, no sharp turns that would register a change in motion. It's a smooth, continuous, and utterly stable journey. Think about being on an airplane. When it is cruising at 500 miles per hour at 30,000 feet, you can get up, walk down the aisle, pour a cup of coffee, and feel no sensation of that incredible speed. Why? Because you, the coffee, the plane, the air inside, everything is moving together at a constant velocity. It's only during takeoff or landing when the plane accelerates or decelerates that you feel the forces at play. Our cosmic journey is like an eternal cruise, an unending flight at an unfathomable speed, but always at a constant, stable velocity within its own reference frame. This continuous, unwavering motion is not just fascinating, it's profoundly important. It's what allows everything on Earth to function as it does. Imagine if Earth's rotation wasn't constant, if it jerked and swayed. Life as we know it would be impossible. The very stability of these constant velocities, the smooth, predictable nature of our cosmic journey, is a prerequisite for the delicate ecosystems, the complex atmospheric patterns, and indeed, the evolution of complex life itself. This is the true marvel of our existence. We are not static inhabitants of a fixed point in the universe. We are cosmic travellers hurtling through the void on a grand, majestic voyage. And this journey is not a chaotic dash, but a meticulously choreographed dance, a breathtaking, cosmic ballet of incomprehensible velocities, where every celestial body from the smallest moon to the grandest galaxy plays its part with exquisite precision. Consider the elegance of it all. The moon, a constant companion, not only creates our tides, but more crucially acts as a gravitational anchor, stabilizing Earth's axial tilt. Without that steadying hand, our planet would wobble unpredictably, leading to extreme climatic shifts that would make sustained life incredibly challenging. The sun, our luminous star, holds us in its gravitational embrace, guiding our yearly revolution, providing the energy that fuels all life. And in turn, our entire solar system is held within the vast swirling disk of the Milky Way, governed by the collective gravity of billions of stars and, most significantly, the invisible scaffolding of dark matter. It's a nested set of gravitational relationships, a harmonious symphony of forces, each layer influencing the next, creating a surprisingly stable and predictable environment amidst such colossal motion. It's a testament to the fundamental laws of physics that govern the universe, laws that allow for such intricate complexity, and ultimately for us. And how did we come to understand this? For millennia, humanity looked up at the night sky and saw a seemingly fixed dome, with stars twinkling like distant lamps. We believed Earth was the unmoving centre of creation, a logical conclusion based on our immediate sensory experience. It took centuries of meticulous observation, groundbreaking mathematics, and the courage of pioneering scientists, from Copernicus and Galileo, who dared to place the sun at the centre, to Kepler and Newton, who unveiled the laws of planetary motion and universal gravitation, all the way to modern astrophysicists peering into the deep cosmos. Remember our friend Léon Foucault? His ingenious pendulum, a simple weight swinging on a wire, provided undeniable proof of Earth's rotation, revealing a truth hidden from our senses. These discoveries were not always easy. They often challenged deeply held beliefs and required immense intellectual bravery. But with each new piece of evidence, with each new calculation, humanity peeled back another layer of the illusion, revealing the dynamic, vibrant and incredibly mobile universe we inhabit. Yet as we stand at this precipice of understanding, we must also acknowledge the vastness of what we don't know. We've spoken of dark matter, the invisible gravitational glue that holds galaxies together, and dark energy, the mysterious force accelerating the expansion of the universe. Together, these two enigmatic components make up an astounding 95% of the cosmos. We can infer their existence through their gravitational effects, through the way they warp light and dictate the large-scale structure of the universe, but we cannot see them, we cannot touch them, and we do not fully understand their nature. What does it mean to know that the vast majority of the universe is made of something we cannot detect, something that remains shrouded in mystery? It's a humbling thought, isn't it? It reminds us that even with all our incredible scientific progress, the universe still holds profound secrets, inviting us to continue our quest for knowledge, pushing the boundaries of human curiosity. It means that our understanding, as vast as it may seem, is still just scratching the surface of cosmic reality. This journey through the motions of Earth and the cosmos isn't just about facts and figures, it's about a profound shift in perspective. It's about recognizing that we are not stationary observers, but active participants in an ongoing, magnificent cosmic drama. Every breath you take, every moment you exist, you are part of an astonishing, multi-layered journey through space and time. The next time you look up at the night sky or even just feel the solid ground beneath your feet, remember this: you are connected to everything. You are part of the colossal spin of Earth, the graceful orbit around the sun, the grand sweep of the solar system around the galactic core, and the relentless march of galaxies through the cosmic web. You're a passenger on an incredible voyage, a testament to the dynamic, ever-moving and utterly wondrous nature of our universe. This profound realization, this shift from perceiving stillness to embracing dynamic motion, is the true gift of science. It transforms our understanding of our place in the cosmos, fostering a sense of awe, humility, and boundless curiosity. We are not just living on Earth, we are living with Earth, moving with Earth on an epic journey that continues silently and majestically every single second. Thank you for joining us on this incredible exploration of how Earth moves. We hope you've been as inspired and awestruck as we are by the hidden mechanics of our universe. Keep looking up, keep asking questions, and never stop wondering. If you've enjoyed this cosmic ride, hit that like button, drop a comment below, and subscribe to Dreamy Science for more journeys into the wonders of our universe. Until next time, keep dreaming big and keep exploring. We've journeyed through layers upon layers of motion, each more astonishing than the last. From our planet's daily pirouette to its annual waltz around the sun, from our solar system's grand sweep through the Milky Way to our galaxy's headlong rush towards Andromeda, and finally our entire local group's participation in the Laniakea supercluster's gravitational current towards the Great Attractor, we've discovered that every cell of your being, every atom that makes up your very existence, is part of a colossal cosmic current moving at an astonishing 800,000 miles per hour, or even... It's a number that truly boggles the mind, isn't it? 800,000 miles per hour! If you were to drive the car at that speed, you'd cross the entire continental United States in mere seconds. Yet here you are, reading these words, feeling utterly still. You're not being pressed back into your seat by immense G-forces, nor are you being flung off into the void. You're simply here, stable, grounded. So how is this possible? How can we be moving at such incomprehensible velocities and yet experience such profound stillness? The answer, my curious friends, lies in a beautiful, elegant principle we've touched upon throughout our journey: constant velocity within a stable frame of reference. Think back to our airplane analogy. When you're soaring thousands of feet above the Earth, cruising at hundreds of miles per hour, you don't feel that speed, do you? The flight attendant can pour you a cup of coffee without spilling a drop. You can walk down the aisle, or even juggle a few oranges, though we don't recommend that mid-flight. Inside the airplane, everything, including you, is moving at the same constant speed and in the same direction relative to the plane itself. There's no sudden acceleration to push you back, no abrupt deceleration to throw you forward. It's a stable environment, a self-contained frame of reference, where the colossal speed outside becomes irrelevant to your immediate experience. Now expand that concept to a cosmic scale. Our Earth, our Sun, our entire solar system, our Milky Way galaxy, and even our local group of galaxies are all incredibly stable vehicles within their respective frames of reference. The Earth itself is a colossal spinning sphere, yes, but its rotation is remarkably consistent. It doesn't suddenly speed up or slow down in a way that would create a perceptible jolt. This constant rotation means that the atmosphere, the oceans, the buildings, and every single one of us are all moving together, in perfect sync with the planet's spin. We are, quite literally, part of the ride. There's no external force within our immediate environment pushing against us to make us feel that rotation. Similarly, our planet's revolution around the Sun is a smooth, continuous elliptical path. While its speed slightly varies, faster when closer to the Sun, slower when farther, these changes are gradual, imperceptible over our short human timescales and completely uniform across the entire planet. We don't experience the Earth suddenly braking or accelerating in its orbit. It's a steady, majestic journey through space. And the further out we go, the same principle holds. Our solar system isn't jerking around as it orbits the galactic center. It's following a stable, predictable trajectory. The Milky Way isn't lurching through the cosmos. It's a vast, gravitationally bound entity, moving as one cohesive unit. Even the local group, as it streams towards the great attractor, maintains its internal stability, its galaxies moving relative to each other, but the group as a whole maintaining a coherent, if incredibly fast trajectory. This is the profound elegance of inertia and a constant velocity. In the absence of a force that changes our velocity, either by speeding us up, slowing us down, or altering our direction abruptly, we simply don't feel motion. We only perceive changes in motion, acceleration or deceleration. Since our cosmic journey is characterized by incredibly vast, consistent movements within nested, stable systems, we remain blissfully unaware of the mind-boggling speeds we're achieving. It's like being a tiny speck on a massive, perfectly balanced top, spinning flawlessly on an even grander carousel which itself is gliding smoothly across an enormous silent stage. Every component is in harmonious, stable motion, creating an illusion of stillness for the speck at its centre. But let's pause for a moment and truly appreciate what this means. This intricate, multi-layered cosmic ballet isn't just a curiosity, it's the very foundation of our existence. The stability of Earth's rotation provides us with the rhythm of day and night, vital for life cycles. The precision of its revolution, guided by the sun's gravity, ensures our temperate climate and the predictable cycle of seasons thanks to that crucial 23.5-degree axial tilt. The moon, our loyal companion, not only orchestrates the tides, but more importantly acts as a celestial gyroscope, stabilizing Earth's axial tilt over billions of years. Without the moon's gravitational embrace, our planet would wobble chaotically, experiencing extreme climate swings that would make complex life utterly impossible. Imagine a world where summers could be scorching hot and winters unimaginably cold, changing unpredictably year after year. That's the reality without our moon. It's a silent guardian, ensuring the long-term stability necessary for evolution and the flourishing of life. And as we zoom out even further, the grand, sweeping motions of our solar system, our galaxy, and our supercluster, all bound by the invisible threads of gravity and dark matter, are not just random wanderings. They are part of a cosmic architecture that has allowed for the formation of stars, the synthesis of elements, and ultimately the creation of planets like ours capable of sustaining life. The universe, in its vastness, is not a chaotic free-for-all. It is an exquisitely calibrated system, a masterpiece of gravitational mechanics. Every spin, every orbit, every drift is part of a grand design. A cosmic symphony that has been playing for billions of years, providing the stable backdrop against which life could emerge and thrive. It makes you wonder, doesn't it? How much of the universe's apparent chaos is actually hidden order? How many more layers of motion and interaction are waiting to be discovered, each contributing to the grand, stable tapestry of existence? This journey has taken us from the ground beneath our feet to the farthest reaches of the observable universe, all to answer a seemingly simple question: how does Earth move? And in doing so, we've uncovered a profound truth, that our perception of stillness is a testament to the incredible, stable dynamism of the cosmos. We are not static observers, we are active participants, hurtling through the universe at speeds that defy imagination, yet held securely within a nested series of stable, gravitationally bound systems. The mysteries, of course, persist. Dark matter, that invisible gravitational glue that holds galaxies together, still eludes our direct detection. Dark energy, the enigmatic force accelerating the universe's expansion, remains one of science's greatest puzzles. These some unseen components remind us that while we've uncovered much, the universe still holds vast secrets, inviting us to continue our exploration, to keep asking questions, and to marvel at the wonders yet to be revealed. So the next time you feel the solid ground beneath your feet or gaze up at the unchanging stars, take a moment to truly feel the cosmic ballet happening all around you and within you. Recognize the miracle of this stable journey, the astonishing pirouette, the majestic revolution, the grand galactic sweep, and the supercluster stream all perfectly synchronized to create the tranquil haven we call home. It's a powerful thought, isn't it? That our sense of peace and stability is not due to a lack of motion, but to an abundance of perfectly balanced, incredibly fast, and harmoniously orchestrated motion. It's a reminder that even in the greatest speeds, there can be the deepest calm. Thank you for joining us on this incredible cosmic adventure here at Dreamy Science. We hope you've enjoyed unraveling the hidden mechanics of our universe as much as we have. What astonishing cosmic fact will you share with someone today? Let us know in the comments below. And if you've been inspired by our journey, don't forget to hit that like button and subscribe for more explorations into the wonders of science. Until next time, keep looking up, keep asking questions, and keep dreaming big. Welcome back, cosmic explorers, to Dreamy Science. We've journeyed through the astounding multi-layered movements of our home planet, from its gentle daily pirouette to its breathtaking dash across the cosmos. We've unraveled the mysteries of axial tilt, the moon's profound stabilizing influence, and the colossal gravitational dance that pulls us through the intergalactic void, all orchestrated by the visible and the unseen dark matter and dark energy. By now, you understand that you, right now, are not ordinary. Not even close. You are hurtling through space at a combined velocity of over 800,000 miles per hour, an incomprehensible speed that dwarfs any earthly vehicle. And yet, here you are, feeling perfectly still, perhaps sipping your coffee, maybe lounging on your couch, utterly oblivious to the cosmic hurricane you're riding. Isn't that the most mind-bending paradox? The grandest magic trick of the universe? We've meticulously charted every astounding layer of Earth's movement, each one adding hundreds, thousands, even hundreds of thousands of miles per hour to our total cosmic velocity. From the Earth's rotation spinning us at over 1,000 miles per hour, to our planet's relentless pursuit of the Sun at 7,000 miles per hour, to the solar system's 500,000 mile per hour gallop around the Milky Way, and our galaxy's 250,000 mile per hour rush towards Andromeda, all while being swept up in the Laniakea supercluster's stream towards the Great Attractor. It's a dizzying, exhilarating ride. And yet you feel nothing. No g-forces pressing you back, no wind rushing past your ears, no sensation of incredible speed. How can this be? How does the universe perform such a magnificent feat of invisible motion, allowing us to build cities, walk our dogs and sip our lattes, all while travelling faster than any spacecraft ever built? Today we delve into the core reason for this profound stillness amid such furious motion. We're going to unlock the secrets of why you don't feel Earth moving, and in doing so, we'll gain an even deeper appreciation for the elegant foundational physics that govern our existence. It all comes down to two deceptively simple yet utterly profound concepts: inertia and constant velocity. Think back to our very first chapter where we briefly touched upon these ideas. Now it's time to truly unpack them, to understand their cosmic significance. Imagine you're on an airplane soaring at 500 miles per hour. Are you pressed against your seat? Is your coffee sloshing around? No, not usually. You can walk down the aisle. The flight attendants can pour drinks, and you can even feel as though you're perfectly still. Why? Because you, the coffee, the flight attendants, and everything else inside that plane are moving with the plane at the same constant velocity. The air inside the cabin is moving with the plane. The floor beneath your feet is moving with the plane. Your body, your internal organs, even the atoms that make you up, are all sharing that same 500 pound per hour journey. There's no relative motion between you and the plane's interior. You are, in essence, part of that moving system. And as long as the plane's speed and direction remain constant, you feel no sensation of motion. Now, what happens if the plane suddenly hits turbulence? Or if the pilot slams on the brakes during landing? Then you feel it. You're jolted, pushed forward, perhaps even slammed and back into your seat. That's because the plane's velocity has changed. It has either accelerated, sped up, decelerated, slowed down, or changed direction. And when that happens, your body, due to its inertia, wants to continue doing what it was doing before the change. If the plane suddenly slows, your body wants to keep going at the old speed, pushing you forward. If it speeds up, your body resists, pushing you back. This is the key, my friends. It's not the speed itself that we feel, it's the change in speed or direction. It's acceleration. Or deceleration, which is just negative acceleration. And guess what? For the most part, within the stable nested systems we've been exploring, Earth and everything on it is moving at a remarkably constant velocity within its immediate environment. Let's break this down layer by layer, building on our understanding of Earth's incredible movements. First, Earth's rotation. We're running at over 1,000 miles per hour at the equator. But everything around you, the air, the buildings, the ground, the very atmosphere, is spinning with you. Imagine you're standing on a massive, perfectly smooth merry-go-round that's turning at a steady speed. You feel no wind, no sensation of spinning as long as you're not looking off the edge. If you throw a ball, it lands just as it would if the merry-go-round was still, barring the subtle Coriolis effect, which is a story for another day. The air inside your room is also rotating at the same speed as you. You are part of Earth's rotational system, and its speed is incredibly constant. There are no sudden jerks, no abrupt stops, no wild changes in direction. Next to Earth's revolution around the Sun. We're hurtling at 7,000 miles per hour. But again, this speed, while immense, is remarkably constant. Earth's orbit is not a perfect circle, it's an ellipse, meaning our distance from the Sun varies slightly and our orbital speed changes marginally throughout the year. We move a little faster when closer to the Sun. However, these changes are incredibly gradual, spread out over months, and are imperceptible to us. Our planet is essentially a gigantic spaceship, and we are its passengers, completely enclosed within its stable environment. The entire system, Earth, its atmosphere, and everything on it is moving together through space. The same principle applies as we zoom out further. Our solar system's orbit around the Milky Way's galactic center at 100,000 miles constant. The Milky Way's rush towards Andromeda at 250,000 miles constant. The what local groups stream towards the Great Attractor constant. Each of these movements, while adding to our total cosmic velocity, occurs within a system where our local environment is also moving at that same steady speed. There are no sudden accelerations or decelerations that would trigger our senses. We are perfectly nested within these stable cosmic conveyances. Think of it like being on a vast, calm ocean. If your boat is moving at a steady speed, and the water around you is moving with the boat, you feel no motion. You can walk around, pour a drink, and feel perfectly stable. But if the boat suddenly speeds up, turns, or hits a wave, you feel it. Earth is like that boat sailing through the cosmic ocean. But instead of waves and sudden turns, we experience an incredibly stable journey, thanks to the immense distances and the consistent gravitational forces at play. This is the beauty of a relative motion. Motion is always relative to a frame of reference. When you say you are still, you mean you are still relative to the ground beneath your feet, relative to the chair you're sitting on, relative to the room you're in. All of these things are part of Earth's moving system. To feel motion, there needs to be a change in velocity, relative to your immediate surroundings. And because your immediate surroundings, the air, the ground, the buildings, are all moving with you at these incredible yet constant speeds, you perceive yourself as stationary. Our senses are brilliantly designed to detect changes in motion, not constant motion itself. This is an evolutionary advantage. If we constantly felt the 800,000 mph cosmic wind, our brains would be overwhelmed. unable to focus on immediate threats or opportunities. Instead, our perception is finely tuned to detect shifts in our local environment, the sudden lurch of a car, the unexpected stop of a bus, the feeling of gravity pushing us down when we jump. These are all those changes in acceleration relative to our immediate surroundings. So the next time someone asks you, "Why don't we feel Earth moving?" you can confidently tell them, "Because we are moving at a constant velocity within a series of stable nested systems, and our senses are designed to detect changes in motion, not steady motion itself." It's a testament to the incredible stability of our universe, isn't it? The forces of gravity, dark matter, and dark energy, while orchestrating these colossal movements, do so with such a profound, unwavering consistency that we, the tiny inhabitants of a small blue planet, can live our lives without ever perceiving the astonishing cosmic ballet we are all a part of. The universe, in its infinite wisdom, has provided us with a perfectly stable ride. This understanding doesn't diminish the wonder, it amplifies it. It makes the fact that we can detect Earth's rotation through something as elegant as Foucault's pendulum even more remarkable. It highlights the ingenuity of human observation, our ability to transcend our immediate sensory limitations and perceive the grander truths of the cosmos. We are not merely passengers on Earth, we are an integral part of its journey, woven into the fabric of its motion. And as we continue to explore the universe, we uncover more layers of this intricate, beautiful dance. The stability we experience, the very foundation of our existence, is a direct consequence of these consistent, immense speeds. It's a cosmic lullaby allowing life to flourish on a planet that is anything but still. But what if these speeds weren't constant? What if the universe wasn't so predictable? What if our journey was full of sudden stops and starts? The very nature of our existence would be impossible. The fact that the universe operates with such elegant, unwavering consistency is not just a scientific curiosity, it's a profound blessing. This cosmic stability, this ballet of constant velocities, is the silent protector of life. It's the invisible hand that cradles us as we hurtle through the void. It allows for the intricate processes of evolution, the delicate balance of ecosystems, and the simple joy of a sunny afternoon, all while we are, quite literally, flying. And with that, we've journeyed through the incredible mechanics of Earth's motion, from the subtle tilt that gives us seasons to the invisible forces that shape galaxies. We've unlocked the secret of why you feel still, even as you ride a cosmic roller coaster. What an incredible journey it has been, exploring the hidden movements that define our existence. If you've enjoyed this ride, if your mind has been blown by the sheer scale and elegance of the universe, please hit that like button, share this with fellow cosmic adventurers, and drop a comment below. What aspect of Earth's motion surprised you the most? What cosmic mystery would you like us to explore next? Join us again on Dreamy Science as we continue to unravel the universe's most captivating secrets. Until then, remember, you're moving, you're always moving, and that's one of the most stable, beautiful truths of all. Stay curious, stay amazed, and keep looking up. And so we find ourselves at the precipice of the truly unknown. We've meticulously mapped Earth's astounding journey through the cosmos, layer by layer, speed by dizzying speed. We've unravelled the elegant physics that allows us to perceive stillness amidst this cosmic ballet. But as we peer into the deepest recesses of the universe, a profound mystery remains, one that dwarfs everything we've discussed so far. Remember our cosmic budget? The universe is made of stuff. We've talked about stars, planets, galaxies, the luminous tapestry we call normal matter. But here's the kicker. All of that, everything you can see, touch, or measure with conventional instruments, every atom in your body, every star in the night sky, every galaxy in the observable universe, only accounts for a paltry 4% of the total mass energy content of the cosmos. Yes, you heard that right. Just 5%. The remaining 95% is shrouded in an enigmatic veil split between two colossal invisible entities, dark matter and dark energy. Dark matter, making up about 27%, acts as the universe's unseen gravitational scaffolding, holding galaxies together, preventing them from flying apart. Without it, the Milky Way would be a scattered dust cloud, not the majestic spiral we know. And then there's dark energy, an even more baffling force comprising a staggering 68% of the universe, relentlessly pushing everything from everything apart, accelerating the expansion of space itself. Think about that for a moment. We, with all our scientific prowess, all our telescopes and particle accelerators, all our brilliant minds, are still grappling with the fact that we can only directly observe and understand a tiny fraction of what makes up reality. It's like trying to understand an entire ocean by studying a single drop of water. So, if we are such a minuscule part of this vast, mostly invisible universe, how is it that we exist at all? How is it that this tiny 5% sliver of normal matter can organize itself into planets, life, and consciousness capable of pondering the very forces that govern its existence? This brings us to the fundamental why behind Earth's motion, and indeed all motion in the universe: gravity. We've spoken of gravity as a force, a pull, something that keeps your feet on the ground and planets in orbit. But what if we told you gravity isn't merely a force in the traditional sense, but rather a profound curvature of the very fabric of space and time? Imagine space-time as a giant taut trampoline. If you place a heavy bowling ball in the center, it creates a dip, a curve in the fabric. Now, if you roll a marble across the trampoline and it gets close enough to that dip, it won't just roll past in a straight line. Instead, it will curve inwards, orbiting the bowling ball, not because the bowling ball is pulling it with an invisible rope, but because the marble is simply following the shortest, straightest path available to it within that curved landscape. This, my friends, is the essence of gravity as described by Einstein's theory of general relativity. The Sun, with its immense mass, creates a colossal warp in the space-time around it. Earth, instead of being pulled by the Sun, is actually falling through this curved space-time. It's in a perpetual elegant freefall around the sphere, tracing a path dictated by the cosmic topography. The Moon, in turn, falls around Earth, and our entire solar system falls around the galactic center, each celestial body following the curves created by the larger masses around it. It's not a tug-of-war, it's a cosmic dance floor, and gravity is the choreographer shaping the very stage upon which the dance unfolds. Every celestial object, from the smallest asteroid to the largest supercluster, is a dancer, gracefully following the contours of space-time, each step an intricate part of the grand design. This revolutionary understanding transforms our perception of motion. Earth isn't just moving through space, it's moving with space. Its path intrinsically linked to the geometry of the universe. And the stillness we perceive? It's not an illusion of stasis, but a testament to the seamless, uninterrupted nature of this cosmic freefall. We are in perfect sync with our environment, constantly falling, constantly moving, yet experiencing profound equilibrium. But what if this delicate balance were to be disrupted? What if gravity, the ultimate orchestrator, suddenly ceased to exist? Imagine, if you will, a universe without gravity. The stars, which are essentially enormous fusion reactors, held together by their own immense gravitational pull, would instantly explode outwards, their constituent atoms scattering into the void. Planets would fly off into the emptiness, continuing in a straight line at their last known velocity, no longer tethered to their suns. Earth, along with everything on it, would rocket off into interstellar space at an incredible 7,000 miles per hour, relative to where the Sun used to be. The very air we breathe would dissipate, no longer held by Earth's now absent gravitational embrace. Oceans would float away. Mountains would crumble. Life as we know it would be utterly impossible. It's a chilling thought, isn't it? It underscores just how fundamental gravity is, not just to motion, but to the very existence of structure and order in the universe. Conversely, what if gravity were too strong? If the initial conditions of the Big Bang had favoured a slightly higher gravitational constant, the universe might have collapsed back in on itself long ago, never allowing galaxies, stars, or planets to form. Or if the Earth's gravity were just a fraction stronger, our muscles might not be able to lift us. Our hearts might struggle to pump blood against the increased pull. If it were weaker, our atmosphere might escape, our bodies might struggle to retain their form. This delicate balance, this cosmic Goldilocks zone of gravitational strength, is what allows for everything we cherish. It's what allows our planet to orbit the Sun at precisely the right distance for liquid water to exist. It's what allows the Moon to stabilize our axial tilt, preventing chaotic climate swings. It's what allows galaxies to form and coalesce, creating the stellar nurseries where new suns and planets are born. So when we speak of how Earth moves, we are truly speaking of a cosmic symphony, a majestic ballet choreographed by gravity. Inertia keeps us smoothly gliding along our path, preventing us from feeling the immense velocities. Constant velocity ensures no jarring accelerations or decelerations disturb our senses. But it is gravity, in its profound manifestation as the curvature of space-time, that dictates the very steps of this dance. It creates the pathways, sets the rhythm, and maintains the elegant equilibrium that allows us to exist, to thrive, and to wonder. Our feeling of stability, that grounded sense of stillness, is not a lack of motion, but rather the ultimate testament to the perfection of this cosmic orchestration. We are not static, we are in a state of harmonious, continuous, and incredibly rapid motion, perfectly attuned to the universal forces that govern us. Every second you are hurtling through the universe, a silent passenger on a colossal, spinning, orbiting galactic vessel, all thanks to the subtle yet immensely powerful hand of gravity. This understanding connects us in a way few other concepts can. Every atom in your body, every particle of dust, every distant galaxy is inextricably linked by this invisible yet pervasive force. We are all participating in the same grand cosmic dance, each movement influencing the next, each orbit a testament to the universe's elegant design. What does this mean for us, the curious inhabitants of this extraordinary planet? It means that our journey of discovery is far from over. The mysteries of dark matter and dark energy stand as towering challenges, beckoning us to continue pushing the boundaries of our knowledge. What further secrets does the curvature of space-time hold? How will our understanding of gravity evolve as we explore deeper into the cosmos? As we look up at the night sky, let us not just see pinpricks of light, but rather the magnificent, dynamic, and interconnected web of gravitational relationships. Let us feel the subtle hum of our planet's rotation, the gentle sweep of its revolution, the grand journey of our solar system, and the majestic flow of our galaxy. Carry this perspective with you, knowing that you are not merely standing still, but are an active, vital part of a universe in constant, breathtaking motion. This journey of how Earth moves has been a profound exploration, a dive into the unseen mechanics that shape our reality. We hope it has sparked your curiosity and deepened your appreciation for the astonishing world we inhabit and the incredible cosmos that surrounds us. If you've enjoyed this cosmic voyage, and if you're as awestruck by the universe as we are, please remember to hit that like button, subscribe to Dreamy Science for more journeys of discovery, and drop a comment below sharing your favourite cosmic fact. We love hearing from you. Until next time, keep looking up, keep asking questions, and keep dreaming, baby. The universe is always moving, always evolving, and always waiting to reveal its next incredible secret. Thank you for joining us on Dreamy Science. Welcome back, cosmic travellers, to Dreamy Science. If you've been with us on this incredible journey, your mind is likely already reeling from the sheer, incomprehensible swords at which you are hurtling through the cosmos. We've peeled back layers of motion from our planet's jaunty spin to our galaxy's headlong rush towards Andromeda. But in our last chapter we ventured into realms even more profound, touching upon the invisible architects of the universe, dark matter, dark energy, and the very fabric of space-time itself. Remember how we talked about gravity not as a mysterious pull, but as the elegant, astonishing curvature of space-time, a concept gifted to us by Einstein. Imagine the universe not as a flat stage, but as a vast, undulating trampoline, where massive objects like our sun and Earth create dimples and valleys. Planets, then, aren't being pulled by the sun, they are simply following the natural curved path of the space-time fabric that the sun has warped. They are, in a very real sense, perpetually falling around it, tracing a majestic orbit without ever quite hitting the bottom of that cosmic well. This isn't just poetic language, it's a fundamental shift in understanding. You aren't merely moving through space, you are moving with space, and space itself is a dynamic, bending, stretching entity. This brings us back to our core question. With all this mind-boggling motion and now this incredible, invisible architecture, why does it all feel so wonderfully reassuringly stable? Why do you perceive stillness when you are, in fact, an integral part of this astonishing pirouette through a curved and expanding cosmos? The answer, as always, lies in the elegant principles of physics, but now seen through an even grander lens. When we discussed Earth's rotation and revolution, we highlighted constant velocity and inertia, the idea that unless there's a change in motion, an acceleration or deceleration, you simply don't feel it. You're moving along with everything else in your immediate frame of reference. This principle holds true even when we factor in the curvature of space-time. Think of it this way. When you're on a roller coaster, you feel the turns, the drops, the sudden bursts of speed. Those are changes in your velocity. But if you were on a perfectly smooth, perfectly straight train moving at a constant 500 miles per hour, and you couldn't see outside, you'd feel as if you were standing still. You could pour a glass of water, walk around, and even play catch, completely oblivious to your immense speed. Your frame of reference, the train car, is moving uniformly. Now, extend that analogy to Earth. Our planet, our solar system, our galaxy, they are all like nested train cars, each moving smoothly and continuously with it as a train car. Earth is a train car in the solar system train, which is a train car in the galactic train, and so on. And the tracks these trains run on, they are not straight lines in a Euclidean sense, but the subtle, graceful curves of space-time. When Earth falls around the Sun, it's doing so at a wonderfully consistent rate within that curved space, a constant velocity along its curved path. There's no sudden jolt, no unexpected swerve, no jarring acceleration in its orbital ballet. It's a smooth, continuous glide, and thus your body moving along with it feels nothing but the familiar pull of gravity, the very ground pushing back against your tendency to fall into Earth's own space-time dimple. But we're not done yet, are we? Because beyond the dance of gravity and space-time curvature, we introduce the most enigmatic forces of all, dark matter and dark energy. These aren't just abstract concepts. They are the unseen puppeteers pulling the strings of the cosmic ballet, dictating the very structure and fate of the universe. Dark matter, remember, is the invisible gravitational scaffolding that holds galaxies and galaxy clusters together. Without it, our Milky Way would simply fly apart. It doesn't interact with light, doesn't absorb, reflect, or emit any electromagnetic radiation, making it utterly invisible to our telescopes. Yet its gravitational presence is undeniable, accounting for about 27% of the universe's total mass energy content. So you're not just moving through space, you're moving through a vast invisible web of dark matter, a cosmic ghost that exerts a profound gravitational influence. Does this invisible influence make you feel anything? Again, why? Because you are moving with it? The dark matter halo around our galaxy, within which our solar system is embedded, is itself a vast diffuse structure. We are effectively floating within this sieve unseen cloud sharing its overall motion. Just as you don't feel the air around you unless there's a breeze, you don't feel the gentle, pervasive gravitational tug of dark matter because you are already a part of its grand, stable movement. It's another layer of constant velocity, a constant uniform falling within a larger, invisible gravitational field. No sudden changes, no perceptible sensation. And then there's dark energy. Oh, dark energy. This is where the universe truly begins to stretch our imaginations. Comprising approximately 6% of the universe, dark energy is the mysterious force that is causing the expansion of the universe to accelerate. Not just expand, but speed up its expansion. Imagine a loaf of raisin bread dough. As the dough rises, the raisins in it move farther apart from each other. The raisins themselves aren't moving through the dough, rather the dough between them is expanding, carrying them along. This is a common analogy for the expansion of the universe. Galaxies aren't hurtling through space away from each other. Instead, the very fabric of space between them is stretching, carrying them farther apart. Now, dark energy is like an invisible leavening agent that's making this dough rise faster and faster over time. It's an intrinsic property of space itself, a kind of anti-gravitational pressure that is pushing the universe apart at an ever-increasing rate. So if the universe is expanding and that expansion is accelerating, why aren't you expanding? Why isn't Earth stretching like a piece of taffy? This is a crucial distinction, and it ties back to our nested systems. While space between galaxy clusters is expanding, local gravitational forces are much stronger. Our solar system, our galaxy, and even our local group of galaxies are all gravitationally bound. The pull of gravity within these systems is far more powerful than the expansionary push of dark energy on those scales. Think of it. The gravity holding you to Earth, the gravity holding Earth to the Sun, the gravity holding the stars in the Milky Way together. These are immense forces. Dark energy's influence only becomes dominant over truly vast intergalactic distances, where gravity is weakened considerably. So while the space between the Milky Way and Andromeda is stretching, the space within the Milky Way itself is stable. Your body, your home, our planet, our solar system, we are all held together by gravity, unaffected by the cosmic expansion happening on scales thousands and millions of times larger than us. We are stable islands within an expanding ocean. This means that while the universe around us is stretching and growing, our local frame of reference remains intact. We are still moving at constant velocities, along curved paths within dark matter halos and inside gravitationally bound system, all while the larger cosmic ocean expands around us. There are no local jerks or stretches that our senses can detect. Our inertia, our constant motion, our connection to our immediate environment, and to all keep us blissfully unaware of the incredible cosmic force play. Isn't that just astonishing? From the gentle sway of a Foucault's pendulum to the colossal unseen gravitational scaffolding of dark matter, from the elegant curvature of space-time to the accelerating expansion driven by dark energy, every single layer of Earth's movement, and indeed the universe's movement, is governed by principles that ensure our stability. We are hurtling through the cosmos at speeds that defy imagination, yet we stand firm, grounded and stable precisely because the universe is a masterwork of consistent harmonious motion. The universe isn't chaotic, it's an incredibly well-orchestrated ballet, a cosmic waltz performed by celestial bodies and invisible forces alike. And you, my friend, are not merely an observer, you are a participant, an integral part of this grand, majestic revolution. Your very existence is a testament to the delicate yet robust balance of these incredible forces. So the next time you look up at the night sky, or simply feel the solid ground beneath your feet, remember the astonishing truth. You're on a colossal spinning sphere, perpetually falling around a star, within a galaxy that's rushing through an invisible web of dark matter, all within a universe whose very fabric is stretching and accelerating, propelled by a mysterious dark energy. And yet you feel stable, you feel grounded, you feel at home. This profound understanding of how Earth moves isn't just about physics, it's about perspective. It's about realizing that the universe is far more dynamic, more mysterious, and more wondrous than our everyday senses can ever convey. It invites us to look beyond the obvious, to question our perceptions, and to marvel at the hidden mechanics that make our existence possible. We've journeyed through the layers of movement, from the local to the cosmic, from the visible to the utterly unseen. We've explored the constant velocities, the inertia, the gravitational balance, the space-time curvature, and the dark forces that shape our reality. And through it all, the answer to why don't we feel it remains beautifully consistent, because it's all so incredibly constantly and smoothly happening around and with us. What an incredible universe we inhabit, a universe of constant breathtaking motion, wrapped in a blanket of perceived stillness. Keep asking questions, keep exploring, and never stop being amazed by the extraordinary reality we share. Thank you for joining us on Dreamy Science. If you've enjoyed this cosmic dive, hit that like button, subscribe for more wonders, and drop a comment below to tell us what part of Earth's movement fascinates you the most. Until next time, keep looking up and keep dreaming big.